Welcome to section 7.2, the ambiguous case. In this section, we have one objective: solve problems involving triangles with an ambiguous case. Well, so far, when solving triangles using the law of science, we've typically known two angles and then sides. So that would be angle side or angle side angle. These cases are where one unique triangle always exists. However, when we are given two sides and an angle opposite one of them, so the side-side angle case, the situation becomes more complicated. This is known as the ambiguous case because there may be one triangle, two triangles, or no triangle at all that fits the given information. So in this section, we will extend the law of sines to handle these side-side angle cases and explore how different conditions affect the number of possible triangles. So when solving a triangle with two sides and the angle opposite one of them, three different outcomes are possible. You could have no triangles, so that means the given information doesn't form a valid triangle. You could have one triangle, where exactly one triangle fits the given conditions, or you could have two triangles, where two different triangles satisfy the given information. So because of these possibilities, the side-side angle is always called the ambiguous case because you could have three different scenarios. So you might also remember from geometry that there is no congruency theorem for the side-side angle, only for the side-side-side or side-angle-side, angle-side-angle, or angle-angle-side triangles for exactly this reason. So side-side angle doesn't guarantee a unique triangle because you could have a case where no triangle exists or more than one triangle satisfies the given information. So how do you recognize these different outcomes, right? There's three different outcomes. How could you recognize which one works for which given information? So suppose we're given an angle A, and the side, lowercase a, so that's the side opposite the angle, and a side B. We can define H as the altitude drawn from the vertex C perpendicular to side B. So in the table on the next screen, it's going to summarize the outcomes in the ambiguous case. So our first column here is the conditions. The second column is the number of triangles that can be formed based off of those conditions. And then the third column is the diagram or a representation of what that might look like. Okay, so in these conditions, we want to assume that we are given angle A and sides A and B in a triangle ABC, and that H is the altitude from C. And so if we aren't given those, then utilizing this table might present a challenge. But as you walk through the problem, you will then be able to utilize other rules that you know in order to state whether a triangle, multiple triangles, or no triangle exists. So in the first row here, if A is less than 90 degrees and A is less than H, your height, then no triangles exist. Another scenario where no triangles exist is where A is greater than 90 degrees, meaning it's obtuse, but the side length of A is less than the side length of B. Three scenarios where you might have one triangle are when A is less than 90 degrees and A equals H, or when A is less than 90 degrees and A is greater than or equal to B. And the third scenario is when A is greater than 90 degrees and A is greater than B. Now there's one scenario here where you can have two triangles, and this is where A is less than 90 degrees and your side length A is greater than H but less than B. So it's like right in the middle, right? And this is a scenario where you could have two triangles. So some steps here to help you solve an ambiguous case problem in case you need it. All right, the first one is to use the law of sines to set up your proportion. Then calculate the altitude if you're given the values that are needed to do so. Then compare your A to H and B to determine whether 0, 1, or 2 triangles exist utilizing the table that we just walked through. You can solve for missing angles and sides based on the case you're working with. And if 2 triangles exist, then you'll solve for both possible triangles separately. Okay? So these would be the steps that you would take to solve your problems utilizing the table. Now, the problems that we're going to work through using the formulas that we know in order to help us. Some problems we'll utilize these steps, and some we'll just utilize the information that we have been given. All right, example 1. In triangle ABC, A equals 35 degrees, lowercase a equals 4, lowercase b equals 12. Find angle B. So that's our goal. So to help us visualize this, let's draw a triangle. So we have A, B, C. Angle A is 35 degrees. Side is 4, side B is 12. Right? And we want to find angle B. So now let's input these values into our sine formula. So side A is 4 over the sine of angle A, which is 35. Side B is 12. We want to find angle B. And we don't know the side C or the angle C, so we won't be utilizing that ratio. So we'll be looking at these two ratios to help us find angle B. So let's use cross multiplication to help set this up. So we'll have 4 times the sine B equals 12 times the sine 35. So sine B equals 12 times the sine 35 divided by 4, which simplifies to 3 times the sine of 35. When we input 3 sine 35 into our calculator, we'll get 1.7207. So this is saying that the sine of B, which we don't know, equals 1.7207. Now we know this value is greater than 1. But when you're taking the sine of any angle measure, its value is going to be between -1 and 1. And since this value is larger than 1, no triangle exists that fits these conditions. If we were utilizing the table in this problem, we would see here that angle A is less than 90 degrees, and A, with lowercase a, which is this value here, and this is B, right? So A here, which is 4, and 12, and 4 is less than 12, right? That would be the first condition on the table. And so here too, you would see, using that table, that no triangle can be formed under these conditions. Right, let's do another one. Okay, example number 2. Find the missing parts of triangle ABC. If A equals 42 degrees, angle A, and side A equals 52 centimeters, and side B equals 64 centimeters. So just like in the last problem, let's draw a triangle 2. help us visualize this. So A, B, C. A is 42 degrees. Side is 52 centimeters. This side is 64 centimeters. Okay. All right. So the first thing that we're going to do is we are going to find angle B. That's the first thing that we're going to do. Because we can use the law of sines to help us because we have the angle A and the side of A. So we'll find angle B. Because we know 52 over the sine of 42 equals 64 over the sine of B. And when we cross multiply, we will have 52 times the sine B equals 64 sine 42. So the sine of B equals 64 sine 42 over 52. Okay. When you enter that right side into your calculator, because we just want to make sure that this triangle exists, we'll get that the sine of B equals 0.8235. That value is between -1 and 1, so it exists. Okay? So now we can take the inverse sine of 64 sine 42 over 52. And we get an estimate rounded to the nearest degree of 55 degrees. Now, 55 degrees happens to be one of the angle measures that will get us a value of 0.8235. We know, according to our acronym here, all students take calculus, that quadrant 2 and quadrant 1 are quadrants where the sign is positive. So there are two angle measures that can get us 0.8235. So we'll use 55 as a reference angle to help us find our other angle. And we'll give that other angle a prime. So B prime will be the angle that will be in quadrant 2. So in quadrant 2, using our reference angle, we'll subtract 55 degrees and we'll get 125 degrees. So we have two angle measures here, possibly for B. Okay. So how does this look then on well, 125 is an obtuse angle. So if we were to make an obtuse angle for B, it would look something like this. This would be B prime, and this would be angle 125 degrees, whereas B would be 55 degrees. But the side length here would be the same. This would not change. Okay, so we now have two triangles that can occur in this problem. All right, so now we need to find the angle C. But we not just need to find C, okay, we also need to find C prime. Okay, so this whole measurement is C, but we also need to find C prime because we have two different triangles. So 1, 2, and then 5, angle C and C prime. Okay. Well, since we know A and since we know B, we can just use the triangle sum theorem to help us find C and C prime. So C will equal 180 degrees minus A plus B. C prime will equal 180 degrees minus A plus B prime, because that's the second term. So substituting in our values, we'll get 42 plus 55. And then for C prime, A and B prime would be 42 plus 125. So C will equal 83 degrees, and C prime will equal 13 degrees. Okay, so we've almost found all of our missing parts. Okay, so the last thing that we need to find are the side lengths. So we need to find the side lengths for C prime and C. So these are all lowercase c's. All right, we just found the angles. Now we need to find the sides. Okay, so let's get a fresh slide to help us find those sides. All right, so let's redraw this triangle real quickly. So A, B, C, we know A is 42, B is 55 degrees. This side is 52, this is 64. You know, this whole thing is angle C, and this whole side is lowercase c. Then for our second triangle, this is B prime. This is 125 degrees, and this is C prime for the angle and C prime for the side. Okay. Oh, and this is 52. Alrighty. Now we can set it up. So our third step here is to find sides C and C prime. All right. So we are going to use the side A and angle A ratio with the side C to help us find our missing sides, C and C prime. Okay. We know from our previous step number 2, that C prime came out to be 13 degrees and angle C came out to be 83 degrees. So let's add that as well. All right. So the ratio for A would be 52 over the sine of A, which is 42. Ratio for C will be lowercase c, because that's what we're trying to find. And the angle of C is 83. For the C prime ratio, it'll be similar. So we have 42 and not 42, that's definitely 52. And then the sine of 42 equals the ratio of C prime over the sine of angle C prime, which is 13. So solving for C, we will cross multiply, getting C by itself. We will divide both sides by the sine of 42. Substituting that into our calculator, we will get C equals approximately 77 centimeters. C prime we'll take similar steps. We will cross multiply. We'll then get C prime by itself by dividing both sides by the sine of 42. So C prime, simplifying, will get us 17 centimeters. Okay? And so now we have all of our missing parts. So triangle, that does not look like a triangle, so I will rewrite that one. All right, triangle number 1 is going to have the missing parts B, which is 55 degrees, C, which is 83 degrees, and the side length C, which came out to be 77 centimeters. Triangle number 2 had the missing parts B prime, which was 125 degrees, C prime, which was 13 degrees, and side length C prime, which was 17 degrees. And that is our answer to this problem. Alrighty. Okay, let's do one more. Find the missing parts of triangle ABC if C equals 37.2 degrees, A equals 105 feet, and C equals 215 feet. So let's draw a triangle to help us visualize this. So C is 37.2, side is 215, and A is 105 feet. And this is lowercase b. Okay. So we're trying to find the missing parts here. All right. So the first thing that we can do is find angle A. How do I know I can find angle A? Well, I have angle C and I have side C, and I have side A, but I don't have angle A. So we can use the two ratios for C and A in the law of sines to help us find angle A. So setting that up, find angle A, we will have 105 over the sine of A equals 215 over the sine of 37.2. So the sine of A will be multiplied by 215 equals 105 times the sine of 37.2. Sine of A will equal 105 times the sine of 37.2 divided by 215. Okay. Now, the sine of A, when we evaluate that right-hand side, is approximately 0.2953. Okay. That value is between -1 and 1, so we know that there is a degree measure that gets us this value. But what degree measure is it? Well, sine is positive in the first quadrant and in the second quadrant. So we have two angle measures. So let's take the inverse of this value to help us find the reference angle. And when I evaluate that, I get 17.2 degrees. So that's one angle measure. A prime, because there's two of them, would be 180 minus A. So that's 180 minus 17.2, which equals 162.8 degrees. Now, if we were to plug this value into our triangle, and this wasn't something that we checked on the last problem, but in this specific one, I wanted to add this extra little tidbit. In this problem, if we take 162.8 and we add it back into our problem, all right, and we say now A is 162.8 degrees, A prime, right? So if we took A prime and we added it to C, we would take 162.8 plus 37.2. We would get 200. Now 200 is larger than 180. Okay. And we know, according to the triangle sum theorem, that all the angles within a triangle must equal 180 degrees, which means then, because this is greater than 180, that this value is not possible. So for this triangle ABC, it's not possible to have two triangles. Okay, so we're only going to have one triangle that fits these conditions. All right. So let's now continue the process, keeping A as just 17.2 degrees. So now we need to find the angle B, and we need to find the side length B. All right. So our triangle here, A, B, C, 37.2, 105. Had to check that real quick. And 215. And we just found angle A, which was 17.2. Okay. So step number 2, let's find angle B, because when we know two angles, we can find the third angle. So B will equal 180 minus the sum of A plus C. So that's 180 minus the sum of 17.2 plus 37.2, which equals 125.6 degrees. Okay. So we now know B is 125.6. All right. So then step 3 is to find side B, lowercase b. So let's use our B ratio. In the law of sines. And let's use our C ratio. So the side C is 215 and the angle is 37.2. Okay, so let's cross multiply. So B times the sine of 37.2 equals 215 times the sine of 125.6. So in dividing both sides by the sine of, by the sine of 37.2, talking faster than I'm writing, we then can evaluate this right-hand side, which then gives us the approximate value 289 feet. All right, so that would be the side length of B. So the only possible triangle for this problem has the missing sides and angle Angle A being 17.2 degrees, B being 125.6 degrees, and the side being 289 feet. Okay. So that contains all of the missing parts of triangle A and B that fit the given conditions. All right, that concludes section 7.2.